Hello and welcome to Sleep Archive. We spend our lives looking up. We build telescopes to peer at galaxies billions of light years away. We send rovers to map the dusty craters of Mars. We map the craters of our own moon with absolute precision. Yet, the most mysterious, unexplored, and extreme environment we know of is directly beneath our feet. The Earth is not a solid, quiet rock. It is a massive, churning heat engine. To stand on the surface of the Earth is to stand on the frozen skin of a boiling world. The ground that feels so permanent and unyielding is actually in constant, violent motion. Beneath our cities and oceans lies a labyrinth of deep caves, crushing pressures, rivers of liquid iron, and a solid metal heart hotter than the surface of the sun. In this series, we are going to dig. We will travel from the fragile, fractured shell we call home, down through miles of crushing rock, into the plastic flow of the mantle, and finally into the roaring magnetic dynamo of the core. We will see how diamonds are forged, why continents are torn apart, and how a swirling ocean of metal deep underground is the only thing protecting all life on Earth from the deadly radiation of space. Prepare to go deep. This is the world beneath. To understand the sheer scale of the Earth, we must start with a humbling analogy. Imagine you are holding a standard apple. If that apple represents the entire planet, the crust, the rock that contains every mountain, every ocean trench, every continent, and every mine ever dug by humanity is thinner than the skin of that apple. The Earth is roughly 8,000 miles in diameter. The crust makes up less than 1% of its volume. We live our entire lives on a microscopic, fragile film of cooled rock. But this skin is not uniform. It is cracked like an eggshell into massive, jagged puzzle pieces called tectonic plates. And these plates are made of two completely different types of crust. The continental crust. This is the land you are standing on. It is incredibly thick, plunging down anywhere from 20 to 40 miles beneath massive mountain ranges like the Himalayas. But despite its thickness, continental crust is remarkably light. It is composed primarily of granite, a coarse, relatively low-density rock. Because it is so light, it acts like a life raft. It is extremely buoyant, refusing to sink into the denser layers below. This is why some of the rocks on our continents are over 4 billion years old. They have been floating on the surface since the planet was born. Beneath the oceans, the story is entirely different. The oceanic crust is radically thin, usually only 3 to 5 miles deep. But what it lacks in thickness, it makes up for in weight. It is made of basalt, a dark, heavy, iron-rich volcanic rock. Because it is so dense, oceanic crust rides much lower on the planet, creating the massive basins that hold our oceans. And unlike the continents, the ocean floor is constantly dying and being reborn. It is heavy enough that when it collides with a continental plate, it gets forced downward, sinking back into the deep earth to be melted down and recycled. Because of this constant recycling, there is virtually no oceanic crust anywhere on Earth older than 200 million years. We are riding on rafts of granite, crashing through a sea of basalt, and beneath both of them lies a boundary that humanity has been trying to pierce for over a century, marking the true beginning of the deep Earth. Just beneath the thin skin of the Earth's surface lies a hidden void. We often imagine the ground as perfectly solid bedrock, but in many parts of the world, it is closer to a rigid sponge. It is riddled with dark, twisting labyrinths that plunge miles into the dark. These are not carved by violent underground rivers or seismic tearing. They are eaten away, molecule by molecule, by the slow magic of chemistry. This process begins in the sky. As rainwater falls through the atmosphere, it absorbs carbon dioxide. As it hits the ground and filters through decaying leaves and soil, it absorbs even more. This mixture creates a very weak, naturally occurring solution called carbonic acid. If this slightly acidic water seeps into granite, nothing happens. Granite is too tough. But if it seeps into a region made of limestone rock formed from the crushed shells and skeletons of ancient microscopic sea life, a chemical reaction triggers. The acid attacks the calcium carbonate in the limestone, dissolving it perfectly. Over hundreds of thousands of years, the water slowly eats its way downward, widening microscopic cracks into fissures, fissures into tunnels, and tunnels into colossal underground chambers. Geologists call this a karst landscape. It is a terrain characterized by sinkholes, disappearing streams, and vast, hidden cave networks. Once the caves are hollowed out, the chemistry reverses. As the calcium-rich water drips from the ceiling of a cave, it hits the open air. The water evaporates and leaves a microscopic ring of calcite behind. Over millennia, these rings stack up, forming stalactites, which hang tight to the ceiling, and stalagmites, which build up from the floor. If given enough time, they meet in the middle to form massive, solid columns of stone. But these beautiful structures hide an environment that is deeply hostile to human exploration. To map the deepest abysses of the earth, speleologists, cave scientists, have to descend into total, absolute darkness, enduring near-freezing temperatures and crushing humidity. The deepest known cave on the planet is the Veryovkina Cave, located in the Caucasus Mountains of Georgia. It is a terrifying vertical drop that plunges 7,257 feet over 1.3 miles straight down into the crust. It is essentially a reversed mountain, a jagged, flooded, pitch-black Everest plunging into the lithosphere. Explorers spend weeks at a time living underground just to reach the bottom and map the flooded sumps where the tunnels finally pinch off. Yet, even at these crushing, sunless depths, the Earth is not dead. In the deepest, darkest pockets of these labyrinths, scientists have found something impossible: life. If you ask a biologist what powers life on Earth, they will point to the sky. For billions of years, the sun has been the ultimate battery. Plants use sunlight to create food by photosynthesis. Animals eat the plants, and predators eat the animals. It is a solar-powered food chain. We used to believe that if you took away the sun, life would simply stop. But the deep Earth is a world that breaks the rules of biology. Deep inside the planet's crust, miles below the deepest caves and the bottoms of the oceans, scientists have discovered a thriving, hidden ecosystem. It is completely disconnected from the sun, the atmosphere, and the surface world. This is the deep biosphere. The organisms that live here are called extremophiles, lovers of extremes. They survive in conditions that would instantly kill surface life. Total darkness, crushing pressures, and temperatures well above the boiling point of water. But if they cannot use sunlight to make food, what do they eat? They eat rock. Specifically, they are chemolitho-autotrophs. This is a terrifyingly long word that simply means self-feeding from chemical rocks. Instead of absorbing photons from the sun, these microscopic bacteria and archaea absorb energy from chemical reactions happening inside the Earth's crust. Take the Mponeng gold mine in South Africa, which descends over 2 miles into the rock. Down there, geologists found pockets of water that had been trapped, sealed off from the surface for millions of years. Inside that ancient water, they found a bacteria called Desulforudis audax viata. This organism survives on the radioactive decay of uranium in the surrounding rock. As the uranium decays, it emits radiation that splits the water molecules apart, creating free hydrogen gas. The bacteria eat this hydrogen and use sulfate to breathe. They are nuclear-powered microbes. Because the energy down there is so incredibly scarce, life moves in extreme slow motion. On the surface, bacteria divide and reproduce in a matter of hours. In the deep biosphere, a single microbe might only reproduce once every 10,000 years. They are essentially immortal, existing in a zombie-like state of suspended animation, waiting for a single chemical reaction to give them enough energy to move. But what is truly shocking is the scale of this hidden world. When researchers from the Deep Carbon Observatory added up all the microscopic life trapped in the pores and fractures of the Earth's crust, the numbers were staggering. The deep biosphere contains up to 23 billion tons of carbon. That means the sheer weight of all these deep Earth microbes is hundreds of times greater than the weight of every human being on the surface combined. We are not the dominant life form on this planet. We are just the icing on a very strange living cake. But even these incredible organisms have a limit. If you dig deep enough, the temperature eventually rises beyond what any carbon-based biology can endure. At that boundary, life ends, and the true, solid geology of the deep Earth begins. If you want to know what is inside a human body without cutting it open, you use an ultrasound or an X-ray. You send energy waves through the tissue and measure how they bounce, scatter, and pass through different densities. To figure out what is inside the Earth, geologists do the exact same thing, but instead of an ultrasound machine, they use earthquakes. When a massive earthquake strikes, it rings the planet like a bell. It releases colossal amounts of energy in the form of seismic waves that travel directly through the Earth's interior. There are 2 main types we use to see underground. Primary waves, P waves, which compress and expand the rock like an accordion, and secondary waves, S waves, which ripple up and down like a cracked whip. By building a global network of seismographs to listen to these waves, scientists discovered something fundamental. The waves do not travel in straight lines, and they do not travel at a constant speed. They bend, reflect, and accelerate. In 1909, a Croatian seismologist named Andrija Mohorovičić was studying the seismic records of a local earthquake. He noticed a bizarre anomaly. The seismic waves that traveled slightly deeper into the Earth arrived at distant listening stations faster than the waves traveling a shorter distance along the shallow surface. It was as if the deeper waves had suddenly hit a cosmic highway. Mohorovičić realized there was only one physical explanation. The waves had hit a distinct boundary line deep underground, where the composition of the rock radically changed. The rock below this line was vastly denser and more rigid, allowing the mechanical energy of the earthquake to travel at a significantly higher velocity. He had discovered the absolute bottom of the Earth's crust. Today, we call this global boundary the Mohorovičić discontinuity, or simply the MOHO. The MOHO is the dividing line between the thin, fragile skin we live on and the massive, churning engine of the deep Earth. It is the direct result of planetary stratification. When the Earth was first forming 4.5 billion years ago, it was a completely molten ball of magma. Just like oil separating from water in a jar, gravity pulled the heaviest elements down toward the center, while the lighter, buoyant silicates floated to the top to cool and form the crust. The MOHO is the exact depth where that crust ends. Beneath it lies a layer of rock so incredibly thick, it makes up 84% of the Earth's total volume. It is a place where the rules of solid matter begin to bend, and where rock begins to flow. When we cross the MOHO and enter the mantle, we encounter one of the greatest misconceptions in all of Earth science. Because volcanoes spit out liquid magma, we tend to imagine the interior of the Earth as a sloshing, subterranean ocean of melted rock. This is completely false. The mantle is solid. It is an unimaginably thick layer of dense, iron and magnesium-rich silicate rock that extends downward for 1,800 miles. It accounts for a staggering 84% of the Earth's total volume. The temperatures here are apocalyptic, ranging from 1,800 degrees Fahrenheit near the crust to nearly 7,000 degrees near the core. At those temperatures, rock should easily melt into liquid. So why doesn't it? Because of the crush. The sheer compounding weight of the miles of rock sitting on top of the mantle exerts millions of pounds of pressure per square inch. This pressure physically forces the atoms of the rock to remain locked together in a rigid, crystalline lattice. The mantle wants to melt, but the gravity of the Earth simply will not let it. However, solid in the deep Earth does not mean what solid means on the surface. Because the rock is trapped at such extreme temperatures and pressures, it behaves in a bizarre way over short periods of time, like the seconds it takes for a seismic wave to pass through the mantle. Acts like rigid stone. It shatters and transmits the shock wave. But over millions of years, the rock exhibits what geologists call plasticity, or solid-state flow. Think of warm pitch or thick glacial ice. If you hit it with a hammer, it breaks. But if you leave it alone for a century, it slowly oozes and deforms under its own weight. Because the mantle can flow, it can boil. At the very bottom of the mantle, the rock is heated by the blazing furnace of the Earth's core. Just like a pot of thick soup on a stove, the hottest rock at the bottom expands, becomes slightly less dense, and begins to rise. It creeps upward at a microscopic pace, perhaps an inch or two a year. It takes millions of years for a plume of hot rock to reach the top of the mantle. Once it reaches the underside of the cold crust, it spreads out, cools down, becomes dense and heavy, and slowly sinks all the way back down to the core to be heated again. These are convection currents. They are colossal, planet-sized conveyor belts of creeping solid rock. And as these massive currents scrape against the underside of the Earth's thin skin, they generate enough friction to drag the tectonic plates along with them. The mantle's slow boil is the invisible engine that rips continents apart, opens up new oceans, and violently crashes land masses together to build the highest mountain ranges on the planet. while the massive convection currents of the mantle move at the agonizingly slow pace of growing fingernails, steadily driving the tectonic plates across the surface. The deep Earth has another, far more violent method of releasing its heat. It does not always rely on the slow, planet-wide boil. Sometimes, the Earth chooses to punch a hole straight through the crust. To understand this phenomenon, we have to look past the creeping flow of the upper mantle, all the way down to the core mantle boundary 1,800 miles below our feet. Here, the solid, pressurized rock of the mantle sits in direct contact with the swirling, superheated liquid iron of the outer core. Because the core is a chaotic, boiling ocean, the heat it radiates upward is not perfectly uniform. There are specific, localized hotspots where the thermal energy transferring into the solid rock is exceptionally intense. When a distinct pocket of rock at the very bottom of the mantle is subjected to this extreme, concentrated blast of heat, its physical properties alter. It expands, becoming significantly less dense and highly buoyant compared to the surrounding stone. It refuses to wait for the slow, creeping conveyor belt of global convection. Instead, it gathers itself into a massive, teardrop-shaped mass of superheated plastic rock and begins to aggressively push its way upward. Geologists call this a mantle plume. A mantle plume is essentially a subterranean pillar of fire. The head of the plume can be hundreds of miles wide, burning its way vertically through the cooler, denser rock of the surrounding mantle. Behind this massive rising head trails a long, narrow tail that remains connected directly to the core mantle boundary, continually feeding the rising column with a steady stream of blistering heat from the center of the planet. They act as cosmic chimneys, bypassing the slow boil of the mantle to vent the deepest energy of the Earth straight toward the surface. When the massive, superheated head of the plume finally hits the underside of the Earth's thin, rigid lithosphere, it acts like a blowtorch. The crust does not just drift apart as it does at normal tectonic boundaries. It literally begins to melt from beneath. The massive thermal anomaly pools under the crust, building immense pressure and liquefying the surrounding rock until it catastrophically erupts. We can clearly see the scars of these deep earth blowtorches on the surface. The Hawaiian Islands, for instance, do not sit on a fault line. They are located dead center in the middle of the massive Pacific tectonic plate. They exist purely because there is a stationary mantle plume blowtorching the Pacific plate from below. As the tectonic plate slowly drifts over this fixed, deep earth pillar, the plume punches a hole, builds a massive shield volcano, and then the plate moves on, forcing the plume to punch a completely new hole. This process, repeating over millions of years, is exactly what created the linear chain of islands. But when a mantle plume erupts beneath a thick continental plate, instead of the thin oceanic crust, the physics change, and the results become apocalyptic. The thick granite of the continent acts like a heavy lid on a pressure cooker. The magma cannot easily break through, so it pools underground for hundreds of thousands of years. As it sits there, it melts the surrounding continental rock, absorbing massive amounts of silica. This silica makes the magma incredibly thick and sticky, trapping volcanic gases until the pressure becomes mathematically uncontainable. When it finally ruptures, it creates a supervolcano. Yellowstone National Park is simply the surface scar of a colossal, active mantle plume currently parked beneath the North American continent. These superheated pillars represent the Earth's most aggressive mechanism for moving material upward, forcefully ejecting the deep mantle onto the surface. But planetary geology is a closed system, governed by a ruthless equilibrium. What goes up must eventually come down. While mantle plumes rocket upward, the immense tectonic plates they help push around are simultaneously colliding on the other side of the world. These violent collisions force massive slabs of cold, heavy crust to plunge back down into the abyss. And as the surface of the Earth is swallowed by the crushing depths, it drags everything on it straight into a subterranean pressure cooker. We usually think of carbon as a surface element. It is the fundamental building block of all life. It forms the structure of our DNA, the wood of the forests, and the carbon dioxide in our atmosphere. But the Earth has a deep carbon cycle, and what the mantle does to carbon is one of the most violent and beautiful processes in geology. As the tectonic plates crash into each other, the heavy oceanic crust is forced down into the mantle in a process called subduction. It drags millions of tons of seawater, dead marine life, and carbonate rocks down with it. As this material plunges deeper, the heat cooks it, and the crushing weight of the planet above begins to squeeze the carbon atoms. About 100 miles straight down at the base of the thickest continental plates, the conditions hit a sweet spot. The temperature reaches 2,000 degrees Fahrenheit, and the pressure hits an agonizing 50,000 atmospheres, roughly equivalent to balancing 80 commercial airplanes on a single postage stamp. Under this specific, localized crush, carbon atoms can no longer exist in their normal, relaxed state. If you look at the carbon in a pencil lead or graphite, the atoms are arranged in flat, two-dimensional sheets that easily slide past one another. That is why a pencil leaves a mark. But 100 miles down, there is no room for flat sheets. The pressure forces every single carbon atom to bond tightly with 4 other carbon atoms in a perfect, rigid, three-dimensional pyramid. This is a tetrahedral lattice. It is the most brutally efficient, tightly packed atomic structure possible. The soft black carbon is crushed into a diamond, the hardest naturally occurring substance in the known universe. But this presents a massive geological problem. Diamonds are forged 100 miles underground. As we will discuss later, humanity's greatest drilling machines have barely scratched 7.5 miles down. So how do we have them on our fingers? We don't mine them from where they are made. We wait for the earth to spit them out. Diamonds are delivered to the surface by the deepest and most violent volcanic eruptions on the planet. Deep in the mantle, a localized pocket of water and carbon dioxide gas trapped in the rock can suddenly become unstable. It expands explosively, liquefying the surrounding rock into a highly fluid, bubbling magma. This magma shoots upward through the crust like a bullet, tearing chunks of the surrounding mantle wall away as it rises. If it passes through a diamond-bearing layer, it grabs the crystals and carries them along. These are called kimberlite pipes. They are essentially deep earth freight elevators. The most crucial part of this journey is the speed. The kimberlite magma rockets toward the surface at astonishing velocities, sometimes exceeding Mach 1, the speed of sound. This supersonic elevator ride is the only reason diamonds exist on the surface. If the magma rose slowly, the gradual drop in pressure would allow the tetrahedral lattice to relax. The diamonds would literally unpack themselves and revert into worthless graphite long before they ever saw the sun. The sheer speed of the eruption freezes the diamond in its high-pressure state, trapping the intense energy of the deep earth inside a cold, clear stone. When you think of an earthquake, you likely picture a fault line right on the surface, two massive blocks of rock grinding together until they snag, build up stress, and violently snap. This is how shallow earthquakes work. The crust is cold and brittle, so it breaks like glass. But as we descend deeper into the earth, the physics of earthquakes face a glaring paradox. We established that the mantle is incredibly hot and under immense pressure. Because of this, the rock behaves plastically. It flows, oozes, and bends like warm taffy over millions of years. If you take a piece of warm taffy and pull it, it stretches, it does not snap. Therefore, deep inside the mantle, earthquakes should be completely impossible. The rock should be too soft to shatter. Yet, our seismographs regularly detect massive, violent earthquakes happening up to 400 miles beneath the surface. How can rock shatter where it is supposed to flow? The answer lies in the violent collisions at the edges of the tectonic plates, specifically in subduction zones. When a dense oceanic plate crashes into a lighter continental plate, the ocean floor is forced downward, plunging deep into the mantle. This sinking slab of rock creates a diagonal line of seismic activity known as the Wadati-Benioff zone. As the slab descends, it acts like a giant frozen tongue thrust into the boiling belly of the planet. Because rock is a terrible conductor of heat, the inside of this plunging slab remains remarkably cold and brittle, even as the outside is surrounded by the searing heat of the deep mantle. For the first 100 miles or so, the core of this sinking plate is still cold enough to snap, creating deep, traditional earthquakes. But as the slab sinks even further, approaching that impossible 400-mile mark, even the cold core of the slab begins to heat up. Brittle fracturing is no longer an option. Instead, the Earth unleashes a completely different, deeply alien type of earthquake. It is called a phase transition. The oceanic slab is largely made of a green mineral called olivine. As it plunges deeper into the mantle, the pressure becomes so agonizingly intense that the atomic structure of the olivine can no longer hold its shape. In a fraction of a second, the crystal lattice of the entire rock violently collapses inward, rearranging itself into a much denser, tightly packed mineral. Imagine squeezing a sponge until it suddenly, instantly crushes into the size of a marble. When millions of tons of deep earth rock suddenly implode and shrink in a microsecond, it releases a catastrophic shockwave. The rock does not break in half, it shatters from the inside out at the atomic level. This transformational faulting rings the planet like a bell, sending seismic waves racing all the way back up to the surface. It is the final, violent gasp of the oceanic crust before it is completely swallowed and melted down by the deep earth. And right below this graveyard of sinking plates lies the true engine of the planet. If you were to drill 1,800 miles straight down, passing through the cold, brittle crust and the slow plastic crawl of the solid mantle, you would hit a wall. It is the most extreme and sudden boundary on the planet, known as the core mantle boundary. Here, the rules of geology completely rewrite themselves. We know this because of how earthquakes behave when they reach this depth. Remember the two types of seismic waves, P waves compressing and S waves rippling. When S waves hit this exact boundary, they vanish. They do not bend. They simply stop existing. Because physics dictates that S waves can only travel through solid material, their sudden disappearance is a smoking gun. At 1,800 miles deep, the solid earth ends, you plunge into an ocean. This is the outer core. It is a churning, violently turbulent sea made almost entirely of superheated liquid iron and nickel. It is roughly 1,400 miles thick. The environment here is so hostile it defies imagination. The temperature skyrockets to between 7,000 and 9,000 degrees Fahrenheit. The pressure is crushing, over 1 million times the atmospheric pressure you feel standing at sea level. You might expect that under such immense pressure, the iron would be forced into a solid state, just like the rock in the mantle above it. But the heat of the core is simply too intense. The thermal energy overwhelms the crushing weight, tearing the iron atoms apart and keeping them in a permanent fluid melt. But this is not the thick, slow-moving magma you see erupting from surface volcanoes. Because it is pure superheated metal under extreme pressure, the liquid iron of the outer core is surprisingly thin. Its viscosity, its resistance to flow, is actually very close to that of water. Imagine an ocean of liquid metal, as fluid as the sea, but thousands of degrees hotter than a blast furnace. And just like our surface oceans, this subterranean iron sea is in constant, violent motion. It is boiling. The unimaginable heat radiating from the very center of the planet rises, heating the bottom of the liquid iron. This hot metal becomes buoyant and rapidly rises toward the mantle, where it cools slightly, becomes heavier, and sinks back down. These are massive, rapid convection currents. There are colossal storms, whirlpools, and jet streams of liquid iron sweeping around the deep earth at speeds vastly faster than anything moving in the solid rock above. This swirling, boiling ocean of metal is the most dynamic layer of the planet's interior. And as we are about to see, the violent motion of this iron sea is the only reason life on the surface is possible. We have established that the outer core is a boiling, swirling ocean of liquid iron. But the Earth is not sitting still. It is rotating at over 1,000 miles per hour at the equator. This rotation introduces a powerful physical force into the deep Earth, known as the Coriolis effect. It is the exact same physics that causes hurricanes in the atmosphere to spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. But instead of twisting thin air, the Coriolis effect underground is twisting an ocean of superheated, liquid metal. As the hot iron boils and rises from the bottom of the outer core, the rotation of the Earth grabs it. It twists these massive rising convection currents into colossal spiraling columns that align with the planet's axis, running from the North Pole to the South Pole. Now, we add the final ingredient, electromagnetism. Iron is highly conductive. When you take a massive volume of electrically conductive fluid and force it to violently swirl and spiral, it generates immense electrical currents. It is the exact same principle as the alternator in your car or a turbine in a power plant, just scaled up to the size of a planet. These spiraling columns of liquid iron act like giant electromagnets. The electrical currents generate a magnetic field, and that magnetic field, in turn, influences the flow of the liquid iron, creating even more electrical current. It is a self-sustaining, continuous loop of physics. Geologists call this colossal, subterranean engine the geodynamo. The geodynamo is the heartbeat of the world. The magnetic field it generates does not just stay trapped underground. It bursts out from the core, punches straight through the mantle and the crust, and extends tens of thousands of miles out into deep space, creating an invisible, magnetic bubble around the Earth called the magnetosphere. This bubble is the only reason you are alive to hear this. Our Sun is essentially a continuous nuclear explosion. It is constantly blasting a lethal, high-speed hurricane of charged particles and radiation in every direction, known as the solar wind. If that radiation were to hit the Earth directly, it would violently strip away our ozone layer, boil away our oceans, and blast our atmosphere off into deep space. This is exactly what happened to Mars. Billions of years ago, Mars had a liquid core, a magnetic field, thick oceans, and a dense atmosphere. But because Mars is much smaller than Earth, its core cooled down and froze solid. The geodynamo died, the magnetic shield collapsed, and the solar wind scoured the planet down to a freezing, irradiated desert. Every second of every day, a silent war is being fought in space above our heads. The solar wind crashes against our magnetic field at millions of miles per hour, and the field deflects it, forcing the deadly radiation to slide harmlessly around the planet. The violent, boiling chaos, 1,800 miles beneath your feet, is the ultimate shield for all life on the surface. But as powerful as this shield is, the geological record shows that it is terrifyingly unstable. The magnetic shield that protects our planet feels like a permanent fixture of reality. Because our compasses always point north, we assume the Earth's geodynamo is a stable, unchanging engine. But the Earth has a memory, and when geologists learned how to read it, they discovered a terrifying truth. The magnetic field is drastically unstable. We cannot see the magnetic field, but it leaves behind a fossil record. We find this record at the bottom of the ocean, in the massive underwater mountain ranges called mid-ocean ridges. Here, tectonic plates are pulling apart, and fresh, liquid magma is constantly erupting from the mantle to create new oceanic crust. This magma is rich in iron-bearing minerals, particularly a magnetic mineral called magnetite. When the magma is molten, it is incredibly hot, well above a threshold known as the Curie temperature. At this extreme heat, the iron atoms are violently vibrating, and their magnetic poles are pointing in random, chaotic directions. But as the magma hits the freezing seawater, it rapidly cools. As it drops below the Curie temperature, the atomic vibrations lock down. The iron atoms act like trillions of microscopic compass needles, physically aligning themselves with whatever the Earth's magnetic field happens to be at that exact moment. Once the rock freezes solid, those microscopic compasses are trapped. They become a permanent, physical recording of the Earth's magnetic field. Because the seafloor is constantly spreading outward from the ridge like a giant conveyor belt, it creates a continuous geological tape recorder. As you move further away from the ridge, you are reading older and older rocks. We call this study paleomagnetism. When scientists first dragged magnetic sensors across the ocean floor in the 1950s, they expected to find a uniform magnetic field. Instead, they found a barcode. They discovered massive, alternating stripes of rock. One stripe would have its microscopic compasses pointing north. The very next stripe, made of slightly older rock, would have its compasses pointing perfectly south, then north again, then south again. The inescapable conclusion was that the Earth's magnetic poles do not stay put, they flip. This is called a geomagnetic reversal. The magnetic North Pole becomes the South Pole, and vice versa. Because the outer core is a turbulent, chaotic, boiling ocean of liquid metal, the electrical currents that generate the magnetic field are not perfectly smooth. They are subject to immense fluid storms and shifting currents. Over time, these chaotic eddies can begin to fight against the main magnetic field, twisting and tangling the magnetic lines of force. Eventually, the fluid chaos overwhelms the system. The main dipole field, the clean north to south magnet, weakens drastically and fractures. Instead of having two strong poles, the Earth suddenly has multiple, weak magnetic poles scattered randomly across the globe. You might have a North Pole in Africa and a South Pole in the Pacific. This chaotic transition period can last for thousands of years. And during this time, our magnetic shield drops to a fraction of its normal strength, allowing vast amounts of solar radiation to bombard the planet's atmosphere. Historically, the Earth's magnetic field flips every 200,000 to 300,000 years, but the last full reversal was 780,000 years ago. We are severely overdue. In fact, our magnetic field has already lost nearly 10% of its strength over the last 2 centuries, and the magnetic North Pole is currently racing away from Canada towards Siberia at an unprecedented speed. The engine is destabilizing, but beneath this chaotic, shifting liquid ocean lies the final, most extreme environment on the planet. For a long time, scientists believed the entire center of the Earth was a vast ocean of liquid metal. But in 1936, a Danish seismologist named Inge Lehmann noticed something strange in the data from a massive earthquake in New Zealand. The seismic waves traveling through the Earth were not just bending as they hit the liquid outer core. Some of them were bouncing back. They were reflecting off something incredibly dense and perfectly round, buried deep inside the liquid ocean. Lehmann had discovered the very heart of the planet, the inner core. If you could survive the journey, 3,200 miles straight down, passing through the boiling outer core, you would suddenly hit a perfectly solid sphere of iron and nickel. It is roughly the size of Pluto, suspended in the exact center of the liquid metal sea. The conditions here represent the absolute limit of planetary physics. The temperature at the center of the inner core is estimated to be around 9,800 degrees Fahrenheit or 5,400 degrees Celsius. That is roughly the exact same temperature as the surface of the sun. At that heat, iron should not just melt, it should vaporize into a gas. But the inner core is not a gas, and it is not a liquid. It is a solid, rigid crystal. This is due to the unimaginable crush of gravity. The entire weight of the Earth, the crust, the thousands of miles of the rocky mantle, and the heavy liquid iron ocean is pressing down on this single point. The pressure here is over 3.5 million times the atmospheric pressure at sea level. This pressure is so absolute that it completely overpowers the thermal energy of the sun-like heat. The iron atoms are violently vibrating, desperate to break apart and become fluid, but the crushing weight physically forces them to remain locked together in a solid, tightly packed crystal lattice. And this frozen heart is not static, it is actually growing. The Earth is very slowly cooling down. As the liquid iron at the very bottom of the outer core loses a tiny fraction of its heat, it dips below the melting point for that extreme pressure. The liquid metal crystallizes and attaches itself to the solid inner core. Every second of every day, the inner core is freezing, expanding outward by a fraction of a millimeter every year. As this liquid iron turns into solid crystal, it releases latent heat. That heat rises up to boil the outer core, driving the convection currents that power the geodynamo and maintain our magnetic shield. The solid heart of the Earth is the battery that keeps the surface of the planet alive. But its slow, relentless growth points toward an inevitable quiet doom. We have sent probes beyond the edge of our solar system. Voyager 1 is currently billions of miles away, sailing through interstellar space. We have walked on the Moon, and we have mapped the surface of Mars with staggering precision. But when it comes to our own planet, we are physically locked out. To understand just how impenetrable the deep Earth is, we have to look at humanity's greatest attempt to break inside. In 1970, on a bleak peninsula in the Arctic Circle, scientists in the Soviet Union began the ultimate geological engineering project. It was the space race inverted. Their goal was to drill straight down, pierce the entire crust, and be the first to reach the MOHO boundary and touch the upper mantle. The project was called the Kola Superdeep Borehole. For 24 years, they drilled. They invented entirely new technologies just for this project, because you cannot simply spin a 7-mile-long pipe from the surface without it snapping under its own immense twisting weight. Instead, they pumped pressurized drilling mud down the shaft to spin only the drill bit at the very bottom. They dug deeper than anyone in history, reaching a final depth of 12,262 meters, about 7.6 miles. To put that into perspective, it is deeper than the Mariana Trench, the lowest point in the ocean. It is the deepest artificial point on our planet. But 7.6 miles is nothing. It is a mere scratch on the apple's skin. It is barely 1/3 of the way through the Baltic continental crust. So why did they stop? They didn't run out of funding, and they didn't hit impenetrable rock. They hit thermodynamics. As you descend into the Earth, the temperature rises in a predictable curve called the geothermal gradient. The Soviet scientists had calculated that at a depth of roughly 9 miles, the rock should be around 212 degrees Fahrenheit, 100 degrees Celsius. They were wrong. The deeper they went, the more the geothermal gradient spiked. By the time they reached 7.6 miles, the temperature had violently jumped to a blistering 356 degrees Fahrenheit, 180 degrees Celsius. At that extreme temperature, combined with the crushing pressure of the thousands of feet of rock above, the granite fundamentally changed. It stopped behaving like solid, brittle stone. It began to exhibit the same plastic, solid-state flow that defines the mantle. The rock became elastic, like warm clay. Every time the drill bit was pulled up to be replaced, the hole simply squeezed itself shut. The deep Earth was literally healing its own wounds. The drill bits warped, the machinery failed, and the physics of the crust made further progress impossible. The project was permanently abandoned in 1992, and today, the deepest hole ever dug by humanity is welded shut under a rusted metal cap. We can look at the stars, but we cannot touch the core. Our understanding of the vast, churning engine beneath our feet relies entirely on the ghosts of seismic waves, the magnetic memories frozen in dead rock, and the violent diamonds spat out by deep volcanoes. But even though we cannot reach the engine, we know exactly how this story ends. The Earth is not immortal. It is a giant heat engine, and like all engines, it is slowly running out of fuel. Every process we have discussed, the creeping tectonic plates, the violent forging of diamonds, the deep earthquakes, and the swirling magnetic shield is powered by a single, finite source of energy, the primordial heat of the planet's birth. When the Earth formed 4.5 billion years ago from a swirling cloud of rock and dust, the kinetic energy of those countless cosmic collisions was converted into heat. Added to this is the slow, steady decay of radioactive elements like uranium and thorium trapped deep in the mantle and core. But the Earth is constantly radiating this heat out into the freezing vacuum of space, and it is losing heat vastly faster than the radioactive decay can replace it. We are living on a cooling ember. As the planet cools, the solid inner core will continue to grow, freezing the liquid iron of the outer core drop by drop. Billions of years from now, the entire outer core will finally drop below its melting point. The swirling, violently boiling ocean of liquid metal will lock up and turn into a solid, silent sphere of crystal iron. On that day, the geodynamo will stop. Without the churning currents of liquid metal, the electrical currents will fade, and the Earth's magnetic field will collapse forever. The invisible shield that protects us will vanish. The solar wind will slam directly into the atmosphere, slowly stripping away our ozone, our oxygen, and our oceans, blasting them off into deep space. Simultaneously, the mantle will begin to freeze. As the rock loses its heat, the plastic, solid-state flow will come to a halt. The colossal convection currents that drive the tectonic plates will stall. The continents will lock into their final positions, never to move again. Volcanoes will go permanently dormant. The deep carbon cycle will end. The Earth will become a geologically dead world. It will look exactly like Mars, a cold, barren rock drifting quietly through the dark, its violent, vibrant history locked forever inside a frozen core. But for now, the engine is still roaring. The ground beneath our feet is still alive, churning with unimaginable heat and pressure, silently shaping the surface world and shielding us from the hostility of the cosmos. The abyss is not empty. It is the beating heart of our home,